Hello everyone. In this session, we will cover the back-end digital design flow using some open source tools. The goal of this session today is to teach you how to perform the back-end digital design using existing open source toolchain. So we will go through the entire process of synthesizing a front-end design that is an RTL or behavioral design to a gate level netlist. This will be done with the software called Yosis, followed by a placement, routing, and layout using the Qflow suite of softwares, and as well as extracting the parasitic resistance and capacitance of this design and perform from the layout and performing the static timing analysis. I would also like to highlight to you the some important output files from these open source tools, that is the .lef, .def, and GDS layout files. These are the geometry file descriptions that describe the geometrical properties, the width, length, height of the metal layers, the position of the transistors in your layout file. So these sets of files are important and interesting because they are a kind of de facto format files that are generated not just from these set of open source tools, but also you will be able to find equivalent or similar file formats from commercial tools such as the Cadence suite of software. The second important class of files relate to the timing parameters of the post layout design. So you can find the timing parameters on of gates of gate paths in the .stf file, and the parasitic resistance and capacitance will be located in the .spef file. We will go through the .stf and .spef files in greater detail in a future session. And finally, I'd also like to highlight to your attention that the tools also generate equivalent SPICE circuit models, which you can then run through a SPICE simulator to get a more precise circuit level, analog circuit level simulation of the chip's performance. But as you can imagine, this step, it's more of a sanity check step. We typically do not run most of the verification tasks in SPICE simulators because this would take too much time. So without further ado, let me jump straight into the proposed tool setup that I prepared for this lesson. Okay, let me share. Let me quickly share the my screen. Okay, I'm taking you to a command line. We will be using an environment called Docker. This is because typically most open source tools are Linux and Unix based, and installing these tools one by one, ensuring that they are working in proper order is a pretty involved task. And today, modern container technologies, Linux container technologies, this is the successor of virtual machine technologies like VMware, allow us to basically package the entire computing environment in a container image. So what this means for you as the user is you only need to install the Docker software. So you can go to www.docker.com, install the software, and then run this command line. And I'll explain a little bit what this command line does. What happens after you run this is that the Docker software will then create a virtual Linux environment using the container that I specify here, that is at pathway stroke Qflow colon 0. So this is a prepared Linux container environment for you that contains all the pre-installed tools that you can just use. So running this command, you run the command docker run. -rm simply means once you exit the container program, it should remove the container from memory. -it simply gives Docker the instruction that you want to actually interact with your container. -v here is basically a mapping. This is my local directory where I have my RTL or behavioral design. Okay, and I'm mapping it to this /data directory within the Docker container. So let me go ahead and run this command to show you what happens. So this is in a Windows environment. You can see the CPROM and okay, this is double RM. You can see a CPROM here, and all of a sudden, I'm now moved into what looks like a Unix platform. And this is basically the Docker container that is running Unix completely. So if I were to just go to the data directory here, I would already see that there's some directories here that have been prepared in advance. And this maps to, this literally maps to, I'll show you my local directory here. So you can actually see my local Windows directory here. Up here, C users, this location. Yeah, okay, right. Okay, so we'll be using this command line, and I'll be showing you a step-by-step of how to use the Qflow software toolchain in order to perform the back-end design portion. In the first step, most of the steps that I'll be explaining to you in the coming minutes are actually derived from this website here. This is the website of Qflow, the version 1.4 digital synthesis flow reference page. So there's some preliminary steps you need to do. That is, you actually have to create a project directory. Okay, in this case, I've already created a project directory called counter, because we will be doing the synthesis, place and route and layout, as well as timing analysis on a simple 2-bit counter design. Okay, and we are supposed to create both a source, a synthesis, and a layout directories. 3 directories have to be created. The Verilog RTL design has to be placed in the source directory, and the name of the Verilog file has to be the same as the name of the top level module of your Verilog design. So the further instructions, if you need some reference beyond this video, you can go to this website. But now let me just walk you through the directory structure that has already been prepared according to these instructions. So we will shift back to the directory. So here, my directory, I have a design called counter. I've created the 3 directories, layout, source, synthesis. Of course, layout is empty. Synthesis is an empty directory. And source contains only one file. It is a system Verilog file, and it's entitled counter. Now let's take a quick look at the contents of this file. So let me switch my screen here. So as you can see, counter is a simple text file. It's a Verilog design, and it's coded in Verilog RTL. You see that I'm instantiating a module, a top-level module named counter, and the top-level module name must be the same as the system Verilog file name. Okay, and I've coded this in register transfer logic style, RTL style, because you can see all the statements are actually updating values into a register called count. Okay, and it's also a behavioral design, because as you can notice, I do not implement this addition using logic gates. I do not use AND, OR, and NOT logic gates. I simply use the behavioral shortcuts like this plus sign. So this is a 2-bit counter, and our goal is to actually synthesize this to obtain a gate level netlist to perform the place, the routing, and the layout. And after the layout has been generated with the Qflow tool, we will actually perform the timing analysis, and I'll show you the locations of all the files. So now that you've seen this, let's go back to the command line so that you can see how this whole process works. So I'm in the project directory. My first command would be to type Qflow followed by the name of the top level module. In this case, it's counter. I enter this, I press enter, and it is telling me that it will use the default technology file, which is the Auckland State University 35 nanometer process. Okay, if you have a different process, let's say you have a process from a fabrication house, or you want to use a more updated 10 nanometer process, you can actually go through Qflow's configuration to point it to these technology files. And why are these technology files important? This is because the process of synthesizing a behavioral RTL code into gate level netlist, we need to actually uh, define the design in terms of standard cell gates. That is, gates that have been pre-characterized and pre-designed by the fabrication. So when we talk about the OSU 035 nanometer process, there are already logic gates within a standard cell library from which the synthesis tools can sort of just draw, and it will craft it, it will actually construct the design based on these standard logic cells, which are comprised of AND gates, OR gates, OR and AND gates, and flip-flops and the like. Okay, so after running this step, we take a look at the directory again. We find that the Qflow has already generated three files, three additional script files, bash script files, the project underscore variables script file, the Qflow underscore executor file, and the Qflow underscore variables file. We will need to modify two of these files before we run them. That is, let's start by modifying the project variables files. So I'm calling my regular text editor. You can notice that the recommended settings have all been printed out, but they're all been commented out as given by the hash sign. So go ahead and uncomment the synthesis, placement, static timing analysis, STA analysis, the router, the migration tool, the layout versus schematic check tool, the design rule check, the GDS tool, and the display tool. The reason we have these is because the tool, the Qflow tool, allows you to use different placement tools, or different static timing analysis tools, or different router tools. And as new tools are created, we can these open source projects can actually allow you to actually utilize those tools instead of the pre-selected ones here. And of course, you can go in and study the Yossi synthesis tool command options, to do optimization, or the placement command options, or the router command options, or static timing analysis options. Just like any other tool, whether it's commercial or process-based, you can go in and actually set your configuration parameters to optimize it. But in this case, for our very simple design to illustrate the concept, we do not need to do this. So we'll go ahead and save this file, and I'll exit. So all I've done is I've looked at the flow options, and I've uncommented the names of the synthesis tools so that Qflow will know which sub-software in the suite to use to perform these back-end tasks. Okay. The next file we will edit is the Qflow executable file. Okay. And this is a file that we will then execute. As you can see, the recommended commands have already been listed here. And these are actually the default commands for all the tools that we mentioned earlier, right? Because these are the default that I've installed and prepared for you. So we'll go ahead and uncomment the Yosis. This performs the synthesis. The Grey Wolf, this performs the placement. The Vesta performs the static timing analysis. Q routers performs the routing. Vesta for static timing analysis is done again. And then there's this design rule check and LVS and GDS generation that is performed. Do not uncomment the cleanup and magic view, because we will not be using the magic viewer in Qflow to visualize our layout files. We will instead be using a different schematic editor. So just uncomment these following commands all the way just before the cleanup. The reason we're not doing the cleanup is I like to show you the contents of the intermediate generated files, because some of these files can actually contain useful information that can be applied to optimize our VLSI backend designs. So go ahead and save the file, exit. So now that I've edited both the project variables and the Qflow executable file, it's time to run the backend IC design process. That is the synthesis to generate a gate level netlist, the placement, routing, as well as the layout generation and then the associated timing checks. What these open source tool suites do not do is they do not insert the additional blocks such as the SRAM and the design for test infrastructure. Clocks are also placed in this thing and in these tools, and of course the power and ground planes are also generated. So for placing the DFT as well as the SRAM tools, you typically have to manually add them in, or you actually rely on more expensive but more high-featured CAD commercial tools. So we'll go ahead and execute the script qflow execute.shell, and this performs the back-end IC design tasks, which is the synthesis, the place, the route, and the parametric extraction for R and C. So we are done, and it's what you will be able to see now. What you've seen just now is actually all the dump from the log files for each and every one of the softwares, but it's not necessary to actually visualize this in the Linux screen. We'll now switch back to the directory that we generated earlier on in the session today. So as you can see now, there's an additional directory that has been created, and this is called the log directory. And here, each of the major steps, for instance, the synthesis step. So if you open the file, so let me just, you will be able to see the qflow log reporting all stages of the synthesis test step, and this is of course using the UOSys software, and you can check whether there have been any errors in any of the intermediate tasks and any of the reports on success or failure of the task, and then appropriately debug it if it's in error. Of course, you have the equivalent log files for route, for placement, for static timing analysis, and post routing static timing analysis, the LVS, the design rule check, and the GDS steps. What is interesting, I'd like to show you a little bit more is the output of the static and the timing analysis file log. The STA actually log file actually would report the max delay and mean delay and clock skew and pin-to-pin delays that it's achievable by your design. Okay, so this is interesting that some of these log files actually have useful analytical numbers in them. But viewing the log dumps is one way to visualize this, but there are also other ways which I'll point out a little shortly. If we look now, if you go back to the source file, you can see that UOSys has generated its own intermediate file, and the synthesis one, all of a sudden, it's full of a combination of Verilog as well as other interesting files. So these are actually post-route netlist, equivalent netlist files, routed netlist files with the power and ground inserted, okay, and so on, right? But I'd like to actually draw your attention to two very interesting files, that is the SDF as well as the SPEF files. So let's quickly take a look at the SDF file. The SDF file contains the timing parameters of each logic net. Let's look at where is the SDF file. Yes, this is the SDF file. It contains propagation timing propagation values for from a particular net to a particular net. So these are propagation delay values of individual wires interconnects here. Okay, in your design after the post place and route. So these are estimated real delays arising from the finite wire length sizes. So the SDF file contains these parameters. And I'd like to now draw your attention also to the SPEF file. So the SPEF file, let me just quickly open it up, contains the parameters, the parasitic resistance and capacitance parameters. Okay, So you can see this is a mapping of individual node names to a shorter reference within the file itself. And here are the basic units of capacitance in femtofarad, resistance in ohms, inductance in henries. So if you go down individual nets, you will see the report of the capacitance values, the report of the resistance values of individual wire connections. And these R and C values, as we'll see in a later part of this course, can be extracted to especially for the critical path to help you to optimize the speed and energy consumption of your design. Okay, moving on. Let's move back to the directory. So we've gone through the source and synthesis directories. We've gone through the log directories, that is the output of the log messages from each of the tools in the Qflow suite. Now let's go to the layout directory. So the most important files in the layout directory pretty much are the GDS file, which contains the final complete layout of the counter circuit, as well as the .def and the .lef file. So there's another file called the .lef. So the .def and lef file contains the dimensions of, is a de facto standard format that contains the dimensions and the positions of the metal layers and all the transistors, and so that you can take a look at that if you like. But I'd also like to show you the output of the GDS file. Now I'm opening the GDS file with another open source layout viewer known as Layout Editor. Let me just switch to that screen now. So as you can see here, this is the complete layout of our 2-bit counter design here. Okay, so you can look at the structure here. There are the 2 output pins here, and the reset and the clock pin at this point. Okay, and you can see that the clock pin, basically looking at the structure, you can sort of see that maybe this is the location of one flip-flop, another flip-flop, and the associated logic, right? Because you see these 2 blocks are similar. Okay, so this is the layout file. You can go ahead and explore this tool to actually see what would be a true real generated layout, and this is a view from the top plane. Okay, moving on, the final set of files I'd like to draw your attention to are the SPICE files. So the backend design CAD tools also generate an equivalent SPICE netlist, and this is netlist that you can actually take into SPICE simulator software like ngSpice. And in here in the layout, this is a SPICE model that is generated of the entire counter design, which can then be simulated with the analog SPICE. And this is typically to check electrical and timing properties, if especially in designs where you're at the cutting edge of the technology and speed. As you can imagine, we do not do verification, most of the verification work in SPICE, although in principle we could, but we do not, because SPICE is much heavier, performs a much heavier computation. It solves differential equations on a very fine-grained time steps, and this is a level of extraction that is much lower than what we need to do in terms of the exhaustive functional verification that most designs obey. So having these SPICE files could be useful if you actually wanted to test maybe up-down transitions of certain of your design, just to ensure that the transitions actually meet meet what you think they are doing, like in terms of their propagation timing, their switching timing, and so on. Okay, the final set of files that I'd like to share with you are in the synthesis directory and under reports, and these are basically the results of the static timing analysis. So static timing analysis is showing the maximum and the minimum delay, because as you can read in the West textbook, when we do synchronous state machines, we have to typically watch out that the propagation from one flip-flop to the inputs of the next flip-flop must obey certain timing parameters. It must actually have propagation delay longer than the mean delay. Otherwise, you will have race conditions. That is, the output actually jumps through 2 flip-flops instead of 1. And you also have the max delay constraint, which is that the propagation must happen uh, within less than a clock cycle minus the setup time. Otherwise, the flip-flop will fail to capture the value in the next round. So just quickly opening up reg to reg max. This is the flip-flop to flip-flop maximum delay. So let's look at that file. You will see that it has identified the exact pathway. This is the name of the nets, the wires, and this is the given delay. And this is actually giving the delay under different transition scenarios. That is the clock transition, transition from this point, this input to this input, and so on. And it also gives you uh, measurements of clock skew. So our design is really small, so we do not see any clock skew here. But supposedly you were to synthesize a much larger design, you will actually have a non-zero clock skew here, and you also will have the setup time of the flip-flop at the destination. And this gives you also the path to fast max delay, as well as the anticipated maximum frequency at which you can run this, you can operate this circuit in practical life, due to the timing requirements, that is the max delay and the min delay, as well as the skew requirements. So you can go ahead and analyze these files in your free time, just to have a sense, but of what the tool can provide. But I really encourage you to start exploring this tool by actually playing around to perform the back-end analysis of designs you can make. And in future assignments in this VLSI course, you'll be required to use these tools in your analysis to actually generate the parasitic resistance and capacitance for the wires, because we'll be doing optimization of the critical paths in circuits. So the key take-home points from this session is you should be familiar with using these open source design tools to perform key steps in back-end digital design, all the way from gate level netlist generation to complete place route and layout generation, plus the associated timing analysis. So feel free to explore and familiarize yourself with the major steps. Thank you.